I'm ready, but I don't see that recording has started, or at least doesn't. Oh, okay, now I see. Yeah, hello everyone. Today is my turn to give some seminar, and it will be mostly about ReactiveMP.jl, but I wanted to make it more like a self-contained tutorial, also about message passing and like basically our methods, what we do. So it will also include some background methods, and I have a notebook about how to use ReactiveMP.jl. Yeah, let me share my screen. Can you see? Good. And I cannot see you, so just in case, unmute yourself and just ask questions. So yeah, let's start. This is our agenda. There's a little bit of background, on message passing and factor graphs, a bit of about our methods, and then we'll proceed with a notebook with a P tutorial. So first of all, I will briefly describe about what ReactiveMP.jl package actually does. So imagine we have some environment of our world, I don't know, and we want to model it somehow. And we have a function PS, and P stands like for our model, and S is our states. And usually this states of our system hidden. So and we don't have a direct access to our hidden states, but we have some observations. So we kind of interact with this world, and we have some observations, and we infer hidden states of our environment. And these observations are usually in some form of data. And in our case, it's like digital data, right? Maybe voice from microphone, or like recording, I mean, whatever. And then we kind of need to come up with some model, and this is sort of a creative process. So, I mean, we don't talk in this seminar how to make this model, but there are a couple of like standard models that we use in our lab. For example, hidden Markov models. They just say that current state of our system depends on the previous state of our system. So here we have like a notion of time, and we have a discrete time steps, and future state depends only on the current state of our system. Then we have this autoregressive models where we assume that the current state of our system depends on like several previous steps, not only on previous, but maybe like two previous steps, or maybe 3 previous steps. It depends. Then we have like hierarchical models where we assume that, okay, current state of our system depends on another underlying process, let's say F, that itself is also another system that can be like hidden Markov model as well. And we also have like mixture models that, yeah, as it says, is a mixture of different models. And then like the problem is that we want to infer the probability of our environment to be in some state, right? And to do that, we need to marginalize all other parameters of our model, all our states, all possible states, given our observations. And usually this problem is unfeasible, so intractable. So we cannot directly compute this integral. And yeah, thanks for your attention. Do you have any questions? Yes. Yeah. Okay, yeah, I'm joking. So yeah, usually, as I said, we have these models in form of a multiplication of several factors, and it makes it a bit easier to compute this integral, because if these factors they depend on a different set of variables, we can decouple this big integral into a set of smaller integrals, and this makes this problem a bit easier. But it's actually still very difficult. I mean, in some situations, it's still very difficult to compute this integral anyway. So we have, we can take a step further, and we can approximate this integral with like another function that we call Q, and we call this Q a variational distribution. And this Q actually is an approximation for this integral, and there's like a paper about it that this Q can be found as a like free energy optimization problem. So we have this function f, and if you just optimize it over all possible Qs, that we find this like the best suitable solution for this problem. And if we don't have any additional constraints on this Q, it just falls back to the original problem. But usually, to make this problem tractable, we set some additional constraints on Q to make this integral is a bit easier to compute. So for example, we can say that, okay, our Q can be only Gaussian, or it can be further factorized, like, etc. And this is like a slide about how ReactiveMP.jl package does this problem. So in a sense, on a very high level, we do this in ReactiveMP. So we optimize free energy functional. But on a low level, we use factor graphs to represent our model in form of factors. And we do message passing to compute this integral. So as you remember this formula with the small integrals, these small integrals actually, we call them messages. And if you know about factor graphs and message passing, you know that these messages are usually depend on a very small set of variables, like 2, 3, 4, 5 maybe, and it's way easier to compute them instead of computing the whole big integral. And this is sort of an outline. So we have a model P. We have a set of additional constraints of our variational family of distributions Q. And Formulab.jl and ReactiveMP.jl, they actually do just an optimization of free energy functional with respect to our model and to our constraints. That's basically on a very high level what happens. And here's a slide about what this ecosystem with ReactiveMP.jl like consists of. We have a GraphAPL.jl package for this high-level and user-friendly probabilistic model specification language, and also for constraints specification. So it's 2-in-1. We have a ReactiveMP.jl that is, in a sense, just a message passing backend. And Rocket.jl is for reactive programming layer for Julia, because ReactiveMP.jl is like written in reactive paradigm, reactive programming paradigm. And of course, we use Julia. It's a high-performance programming language. And in order for you to try this package, you actually need all of this. So you need Julia, and you need free packages. I also advise you to install like distributions.jl, like this miscellaneous packages. And yeah, of course, it's available on GitHub, and it's registered in general Julia package registry. So it's just possible just to add these packages from standard Julia package manager. So at this point, I will proceed with a notebook about API. So if you have any questions about like background and methods, maybe you can ask it now. Okay, I assume there are no questions. Can you see my screen? Cool. Cool. So I really hope that there will be no any issues. I didn't run this notebook today, but yeah, we all know about this presentation effect. So maybe something will. Again? Zoom. More? Yeah, like this. Yeah, everyone can see it, or otherwise I can zoom it even more. Okay. So yeah, now here we see a famous Julia compilation times. Just in case the Julia compiles everything just once and then it's fast. But for the very first time, it kind of lags a bit. So this notebook, it covers the fundamentals of the ReactiveMP.jl package. It doesn't do like a lot of advanced stuff. It actually, this package can do way more than described in this notebook. But this is more like just to introduce you what it can do. But for like more rigorous introduction, I will just refer to the documentation. So again, as I said, we have this GraphVPL.jl package for model specification and for constraint specification. But for now, we talk only about model specification. So we have this model macro that creates a probabilistic model for you. And it actually looks like this, and it's very close to Formulab.jl, except that we have only one macro and we have a function for our model. And this function, it's just a regular Julia function, may accept any arguments. And this model macro also returns you the same function, right? And in this function, we can use tilde expressions to represent the conditional dependencies between variables in our model. For example, to create a random variable, we use random var function. And it just creates a random variable for us. Then we use a tilde expression to say that, okay, S is sampled from Gaussian with mean precision parameterization. And we have these arguments here in our function, and we can pass it here. So here I assume that S mean and S precision are constants. We have a data var function to represent our observations. So in Formulab.jl, for example, we use a placeholder function for that. Here we need to create data variables in advance if we want to use that. And we also need to specify type of our observation. So in this case, I say that, okay, Y is our observation, and it has a type of float 64. It's built in Juliet type. And I say that, okay, Y is sampled from also Gaussian mean precision, but mean is modeled by S, where S is a random variable. And I also return S and Y for later usage. It's very convenient to return some random variables and data variables from our model just for later usage. And this model macro, it modifies this function accordingly to create a factor graph for you. So basically it just creates a factor graph, it does nothing else. So there's no inference yet. And it is modified, so return value is modified a bit. So instead of just returning S and Y, this function also returns a reference to our model as a first argument, and everything else you returned from your function as a tuple. For example, if I add something else here, it will be returned here. So A will be equal to 1. Okay. So now we can create our model. And we have some like helper functions to help to analyze this model. For example, get nodes just returns an array of factor nodes in the corresponding factor graph. So if I call it, it should return me 2 nodes because we created 2 nodes, Gaussian in precision here and Gaussian in precision here. So, and indeed, it's just 2-element vector of abstract factor node. And we can just examine it. Yeah, I will not go into details here, but yeah. Here, for example, we see that our node is stochastic. It has like 3 interfaces and etc. We have our functions like get random, get data, get constant, just to get some insights about our model. For example, we have one random variable named S. We have one observation named Y, and we have a set of constants in our model. Like 0, 1, 1. So here, for example, 1 here, and 0, 1, I passed it here. So as I said, it's just a regular Julia function. So in principle, any valid Julia code can be used inside this model function. I mean, I know that there are a couple of issues. For example, if you do something like this probably won't work. For example, a function returns several values. but it just needs to be fixed. So the fix should be relatively easy. So for now, that probably won't work, but it's not a big of an issue. So basically, you can use like if blocks, for blocks. Let's just examine this model a bit. So here I create a sequence of random variables S. So random var accepts an additional argument N, and this creates a sequence of random variables. So it's very convenient to use it for state space models because we usually have this sequence like in time, right, in discrete point of times. And the same for data var. So I create a sequence of observations. And in this model, it's just a simple state space model. I think it's a random walk, yes. So we have a prior on our first state. And we say that, okay, our observation is just a noisy state. And then we have the following statement. It says that the current state of our system depends only on the previous state of our system. And we have a noisy observation here, just a classical random walk. And we create our model, and we can create our model, and we can see that it creates 20 nodes in this case. It creates 10 random variables, 10 observations, and a set of constants. And you can actually use complex expressions inside this tilde expressions. So, and it will automatically decouple your expression. So in this case, it will create a multiplication node for you and a plus node for you. So it's kind of automatically unroll these complex expressions into free tilde expressions. The only one exception is the indexing expression. So for example, this doesn't create any extra nodes, but in principle, in Julia, this brackets, it is a function. So this is actually the same as something like this, right? But this get index is the only one exception. And also this tilde operator, it automatically creates a random variable for you if none was created before. So as random var is optional actually, so we can directly create it with our prior. But sometimes random var is convenient, as I said, in this state space model, so we can create sequence in advance. And also, for example, this model macro tries to catch some errors. For example, if you created this variable before, so here in this example, S is not a random variable. And we say that, okay, S is sampled from Gaussian, and it will just throw an error in this case. So any questions so far? Okay. Also about constants, let's talk about the constants a bit. So by default, GraphPPL.jl, as you may notice, it here in this model, it created 21 constants. And this is because GraphPPL.jl by default creates a new constant every time it sees some literals. So in this case, it creates 0.1 every time. So for every state, it creates 1, 1, 1, 1. So it will be a lot of ones. But there is a special helper functions for that function. It says constvar. So we can create a reference for our constant in advance. So it will be a little bit more efficient in this case, especially if this constant is a matrix. So we don't want to create copies of these matrices like in our sequence. We can just create this reference once and just reuse it. All right. So here you can see that I pass these matrices as arguments to our model, and I just create like a constant reference for it for our model, and I reuse it. Also, tilde expression can return a reference to a newly created node. So the syntax for it is the following. So in that case, we can just just get the reference for Y node. Might be convenient for later usage if you want to specify initial joint marginals for your node, but that's yeah, we'll talk about it later. But just in case, if you want a reference to your node, you can just get it. And you can also do something like this. So for example, you can create a vector, and you can say that, okay, first is a Gaussian. I mean, you just need to maybe create like 10. So you can do something like this. So it will automatically put your node in this array. Okay, this is about our model specification. So how do we do inference in ReactiveMP.jl? So ReactiveMP uses Rocket for inference routines, and Rocket is a reactive programming extension for Julia. It is highly inspired by Rx.js, if someone is familiar with that, or just similar libraries from Rx ecosystem. And it consists of observables, actors, subscriptions, and operators. And like for more information, there's a GitHub page for Rocket.jl, and it has a huge documentation about all aspects of reactive programming. So here I just show a simple example. So observables are like, you can think of it as a so we have an array, right? Just imagine an array, and it has some values, sequence of values, and we can directly pull some value from that array. Like for example, we use indexing for it. But with observables, we cannot do that. The only thing we can do with observables is to subscribe on future updates. And we cannot directly pull any values from that observable. It will notify us automatically when new value is available. So for example, I create a timer observable, and what it says that it emits a new value every second, and it has an initial delay in 1 second. And in order to subscribe,
I'll count here.
Okay. In order to subscribe to this observable, we need an actor. It's like in this case, we use in the form of a callback. So we can imagine that when every time new value is available, we just call a pre-specified function. And in this case, we just print it. So if I subscribe on it, you see that every second it does something, right? But my notebook is it isn't blocked. I still can do something with it, right? But printing will be a bit strange in this case. But anyway, it's like a synchronous execution. So this observable still runs somewhere, right? And it delivers my values. And it's like an asynchronous execution. And in order to stop all of this mess, right, we need to unsubscribe from it. So it is very important to unsubscribe from observables because they will just keep running otherwise. And we can modify our observables. For example, here I use operators. So in this example, I have my initial observable, which is timer here. I filter. So here we have only odd values, and I map them to be like squared. Right, and I can also subscribe on this modified observable, and we can see that indeed we have only odd values and they're squared. But we also need to unsubscribe. So this is the general idea of observables. So we have some streams of data, they deliver our values, and this is have huge consequences on the API itself of ReactiveMP.jl. So in ReactiveMP.jl, everything is an observable. So we have posterior marginals, for example, and they are in form of an observable. So we cannot directly pull the value of a marginal, but we can subscribe on its future values, right? And every time we have a new data, we pass this new data to our model, and we get an update for our posterior. So this is the general idea. And there are two functions for to obtain an observable of our posterior marginals. Get marginal just pulls one single random variable and creates an observable of marginals for that variable. And also, if you have a sequence of random variables, so each posterior returns us a stream of future updates, and this function get marginals with s at the end. It transforms an array of observables into an observable of arrays. Right? It's like because every posterior returns each individual value in the form of a different observable. So we need like there is a special operator that casts an array of observables to an observable of arrays, and they are synchronized. And let's see how it works in practice. So here we have a simple coin toss model. So we assume that we have n coin tosses. And we assume that they're coming from Bernoulli distribution with theta parameter. And we also don't know this theta. So we say, OK, let's say that this theta is sampled from some beta distribution, and this 2 and 7 are just random. I don't know. I don't have any prior about the bias of my coin. So that's how we do it. So basically, this is a simple model. Any questions so far?
A small reminder that you actually have a prior, right, for your bias in form of that.
I mean, 2.0 and 7.0 are just random values. I mean,
you just chose them out of a hat.
Yeah, I mean,
it does mean that you have a prior belief that the coin will be biased. And it kind of represents that you have 2 observations of head and 7 observations of tail kind of already made. But it doesn't matter.
I mean, yes, Alp, yes.
Do you have something like a wake prior on this ReactiveMP model that you can just specify? I don't have anything on so let's make it uninformative.
There is a wake function, for example, wake, right? Normal mean variance that returns you a wake distribution over some distribution, right? So in this case, we have this Gaussian, zero mean Gaussian with huge variance. But you cannot use that in model specification. So in model specification, if you want to do that, you need to specify it by hand. So in this case, it would be something like, yeah, something like that, right? So this is a vague prior. Yeah, this is the reason for that is because some distributions, they don't really have one vague prior. So when we talk about vague, we usually mean uninformative. And for example, gamma distribution has like 3 uninformative representations, as far as I remember. Maybe, I mean, at least 2. And this is basically up to you, right? So you need to do it by hand in model specification.
Okay, thank you.
But for example, in your code, if you need somewhere vague, you can use vague function for that. Right? And actually, there will be an example later on. So yeah, here we create our model. So this underscore here, it actually says just ignore. So in Julia, if you use underscore somewhere, it just ignores this value. So, but essentially here we have a reference for our model. But I'm not really interested in that now, so I just ignore it. And we have a reference for our data variables and theta parameter. So let's create this model. And so, yeah, in order to get a posterior marginal for our theta parameter, we need to subscribe it. And yeah, we call this get marginal function. We pass our callback to it, and in this callback we just print it. I mean, we don't do anything special, but the idea of this API, like on a very high level, is that you will have a continuous stream of data, And this continuous stream of data will continuously update your posterior marginals, and you can do some actions, right? Every time you get a new posterior, you may decide to do something. And this is like an infinite process, right? In real applications, you actually will never unsubscribe. But for testing, we just do printing here, so we don't do any like complex actions, and we have a static data sets. So we also unsubscribe. So, okay, I subscribe on our marginal, but it doesn't do anything yet, right? It's just a subscription. We don't have any data. So let's create some data set, and we have a bias in our coin. Let it be 0.75. We generated like synthetic data, synthetic coin tosses from Bernoulli distribution, and we can pass our data to our model, and we do it with update function. So update function, it supports two regimes. So in case if y is a single data var, it will just pass this data to this point. In case if both y and dataset are arrays, it will pass one by one, right? So for every data var, it will pass one single data point from dataset. So for convenience here, y is an array because we created it with data var and with argument n. And dataset is also an array because we generated 500 points. And we can see that when I pass my data, I immediately get an update, right? So, and I specified this update here actually. We don't have any printing in this cell, but this update function actually enforces inference backend to compute this posterior marginal, and this update force print line function. And for example, you see if I unsubscribe and if I update, nothing happens because inference backend is lazy. It doesn't do anything if no one is listening for this posterior marginal. So in this case, our data is lost. So because inference backend just ignores it. And if we want to do something, we actually need to subscribe on this posterior margins. Any questions? Okay. So for convenience, Rocket.jl provides some useful built-in like actors or callbacks. So in this case, we use print line function just by hand. But usually when we test our models, we want to keep these marginals in some sort of a storage or an array. And Rocket.jl provides like some handy actors for that. For example, one of them is keep. And keep accepts an optional type argument. So in this case, I create an array. Basically, it's just an array, but just a reactive array. So basically, something like this. And I can pass this theta values into my subscribe function, right? And this theta values will just store every update in its internal storage. That's it. That's all what it does. So in this example, I again subscribe on our posterior marginals, and I use a take operator. It takes one value. And the reason for that, the reason it works is actually because marginal observable always keeps the last update. So every time, so for example, when inference runs, this observable always caches the last value. And when something else, some new actor subscribes to this observable, it immediately gets this last update. So this is basically it. In this example, we just observe the very last update. All right. And we can see that. Oh, Albert. Okay, you have a question.
But yeah, just a small question. This take one, is it a function of what? Take actually.
It's an operator of a reactive operator. So, okay. For example, I hope we have this observable here. Right. Okay. So, and as you remember, it was an infinite stream of data, right? I need to unsubscribe from it. But if you just take, like, I don't know, 3 values from it, it will just unsubscribe automatically. You see, so I don't need to unsubscribe from it. And take is another operator. So, as I said, Rocket.jl like has this big documentation, and it has a bunch of operators, like a lot. And take just one of them. And logger actually is also one of actors. And instead of just doing like print line, right? I can just pass logger to it, and it will do it automatically.
Okay. Yeah, thanks, I see.
And in this case, for example, take 2 will do nothing because we have only one cached values, only last. So in this case, I just do take 1. And as you can see, after I called this function, I got this last value, right, in this vector. And if I do it again, it will have 2 values because it actually because it stores all of them, right, no matter what. In comparison, we have a buffer operator that stores not like all updates, but only the very last update. And it is useful to use it for state space models where we use variational message passing. A bit later about that, but the idea is that we do a lot of variational iterations, right? And on each iteration, we do have a new value. But we only interested in the very last one, so we kind of use buffer operator for that. So as an example, I create buffer actor here. I subscribe once, I get this value. And if I subscribe again, it will just overwrite this value. So I have only 1. But I mean, this is what we usually use when we do inference procedures, and you will also see this keep actors later on. So any questions so far? Okay. So here's a bit of example how to do a reactive inference, that what I talked about, like continuous streams of data and continuous updates. So this is the same model essentially, but instead of having like static data set with n data points, we have an online setting. So we'll learn with every new data point. And for that purpose, I do have a prior for our theta parameter, and I do have an observation here. So model is essentially the same, it just has only one observation at a time. And I create this model, and here I say, okay, every time we have a new marginal update for our theta, we are going to use it as a prior for our next time step, for our next observation. Right, and we also going just to, and we also print it. Yeah, here we can do whatever we want at this moment, but the essential here is that every time we got a new posterior, we use it as a prior for our next data point. Right, so I can subscribe. Nothing happens at this moment because we don't have any data points or updates. Here, our initial prior, it's actually, at this point, it's random. Right? It's not 2.0 or 7.0, but it's just random. And we have a data source. And this data source, again, just emits some points, every half a second. But timer initially it sends like sequential numbers, like 1, 2, 3, 4, etc. And I use a map operator to transform it to actually coin tosses. And I also use a tap operator that just taps basically a side effect. So every time I have a new observation, it will print it here. Okay. And so at this point, we can subscribe to our data source. And every time data is available, we pass it to our model as our observation. And what happens? So we have a new observation, and every time we have a new observation, our posterior changes and our prior changes, and etc., etc. And this is a continuous process, right? It never ends. So, and this is what actually kind of an idea behind this API, the whole reactive API. Where I am? Oh, okay. So, and this will never end unless I unsubscribe. But this is actually the purpose, right? We don't want it to end if we have like some agent. It will continuously and it will never end. It will just perform some action over and over again. But for testing, we can just unsubscribe and just release our computer resources. And so that these models, were an example of some product algorithm or belief propagation. So we didn't impose any additional constraints on our variational family of distributions Q. So we just actually directly computed this huge integral right from the beginning of my presentation, because the problem is simple and it's possible to compute that. But in most of the cases, we actually can't do that. So we need to impose some additional constraints in our model. And for that reason, we have this optional where clause for every node in our model specification. So here, a simple model of IID Gaussian observations. So we have a set of observations. They are independent, but they identically distributed from Gaussian with the same mean and with the same precision. But we don't know the exact value for this mean and precision, so we also create random variables with some priors. And this is actually some vague priors as well, so I don't have any prior knowledge in that, but we need to set some priors. And in order to solve this problem, so we cannot use some product here. So, but we can use a mean field assumption on our variational family of distributions Q. And to enforce mean field, we use this where block with Q here. And we additionally factorize our like local Q. So if you look at beta factorization is here. It consists of local node like Qs and variable local Qs. And then in this case, by default, Q is equal to something like this. And this corresponds to some product. But as I said, we cannot solve it. So we additionally impose an extra factorization constraint on Q. So we decouple these variables. So it makes this problem a bit easier so we can solve it. But of course, every new constraint in your model leads to like poor approximations, let's say, right? And so there should be a balance between a lot of constraints and like accuracy of your posteriors, because yeah, sometimes you may like do some ridiculous constraints that actually and it will just gives you a wrong answer. It will of course compute, but it will be just wrong. Right, for example, we discussed recently with oh, Ismail has a question. Okay.
I don't have a question, but I noticed that there needs to be an inverse in this markdown for the beta factorization. You need to have an inverse for the QISI.
QI, yes, here you mean. Yes, that's a good catch. Like this.
Yeah.
Good catch. So yeah, actually we discussed recently with Ismail, for example, if you do have a random VOC model, it doesn't make a lot of sense to do a mean field approximation because actually they are connected. Every state in your random VOC is connected, and if you decouple it with mean field, it just will give you a very poor approximation. So structured is way better. but the biostructure is a bit later. So here we have our extra constraint on Q, and we can create this model, and GraphPPL will automatically like encode this information in a factor graph. And in comparison with Formulab, so Formulab actually does this extra factorization constraints globally, right? But in ReactiveMP, we use this beta factorization, and we specify this factorization constraints locally for each node. But essentially, it's exactly the same, just a bit of a different like point of view, but it's exactly the same. So this variable block supports different like options, how you can specify. For example, you can specify min field using the same variable names as you use in your expression. Or you can use actual names of these variables. Right, for example, here out represents for an out edge of a Gaussian node, mean edge and precision. Or for min field, you can use an alias. If you don't want to actually type all of this, you can just say min field. There is also an alias for sum product, full factorization. So this is an alias for sum product. And in the same way, you can specify structured factorization. So min field decouples all variables in your local structure, but you can preserve some structure here, right? So in this case, like output of our node and the mean are structured in one joint marginal. So this is basically how you specify structure. Also, on a global level, model macro accepts a set of options. So it accepts like an array of options, and one of these options is default factorization. So you can just specify that default factorization is a min field. So for any node in your model, so just use min field. Any questions? Okay. So yeah, let's run inference in this model. We have a data set. So as you can see, I just sample 1,000 points independently from a Gaussian with mean equal to -3 and with precision equal to 5. So normal from distributions.jl accepts standard deviation as its second argument. So to convert precision, I just take square root of it and inverse. So, and we have some data set. We again create our model. And in this case, we do variational inference. And because of that, because variational inference is an iterative procedure, we need to do many iterations, and also we need to start from something, right? So, for example, let me skip the set marginal for now. And I will do inference, and I get no results. Because my inference backend, it doesn't know where to start from, right? So for that reason, we have this set marginal function. What it does, it initially set an initial posterior marginal for your random variables. And here I use actually wake function because usually it doesn't really matter where you start from. I mean, in some super complex models, it matters. But in this, it doesn't really matter, so we start from wake. And I also use keep actor here, just because I want to keep all values of my mean and my precision. I subscribe on marginal, I pass these actors here. And to do a single VMP iteration, we need to update our data once. But to do multiple VMP iterations, we need to update the same data multiple times. So it actually will enforce our backend to recompute posteriors every time again and again. using the same data, so it will just update our posteriors. And I mean, eventually it should converge, right? So and to check the convergence of our procedure, we use a free energy, and about free energy later. So okay, we compute, and okay, I get some values for our for a mu, and as you can see, it changes, right? With every iteration, it changes a bit, and eventually it converges to some stable values. I mean, relatively stable, but it's probably numeric. So, and the same for our precision. And we can observe last values, last posterior, and we can see that mean indeed converged to -3 as expected, and precision converged to 5 as expected, with actually pretty good accuracy. So the model is very certain about these parameters. Any questions so far? So GraphPPL also supports form constraints for individual posterior marginals. So in a previous case, we specified constraints for QAs, right? It's a factorization constraints basically, but we can also specify constraints on QIs. The QIs is they are individual posterior marginals or over all variables in our model. And we can say, for example, I want QY over some variable to be Gaussian, as I said, or to be gamma, or to be something else, or to be a point mass. And to do that, we also use a var block. But we need to create this random var. So we need to call this function, random var. And to that function, we pass form constraint. And in this case, I say, OK, we have this model, but I want our mean to be a delta function. So this is no longer a Gaussian distribution, but it is just a delta function. So in a sense, it is an expectation maximization algorithm. And we also have the same factorization constraint for our observations. The only difference in this model is that mu, it's a random variable, but it has a form of a delta function. So it's here again. I'll just fix it. So okay, we create it again. We run our inference. And as you can see, now marginal over our mean is no longer a Gaussian distribution, but it's a point mass, right? And it has no variance, or it has no standard deviation. It's just one single point -3. I mean, we kind of lost this information, right? But this example is for demonstration purposes. In this example, of course, it's not necessary to enforce mean to be a point mass, but just for demonstration purposes. Sometimes, for example, in gamma mixture experiments, we had this as well. So for during an inference, we didn't have an analytical solution for some variables in our model, so we just enforced them to be point mass, and we used an like optimization library to optimize over their log PDFs just to find the mode. Yeah, there are a lot of cases where you eventually need this feature, not in this model. Okay, so yeah, as you remember from factor graphs, right, to compute a posterior marginal over some random variable, we compute a product of two colliding messages on an edge, right? And every edge corresponds to some random variable in your model. And by default, ReactiveMP.jl expects that this product available in closed forms in closed form. So we have an analytical solution. And in some cases, for example, if messages are Gaussians, this closed form is available, and it's easy to compute. For gamma distributions as well, basically for conjugate families of distributions, this product exists. And by default, ReactiveMP expects that this product is available. And it will just throw an error if it can't compute an analytical solution for this colliding messages, if it can't compute a product. But it is possible to disable that, basically to enforce inference backend. Instead of throwing an error, just keep propagating this product in form of a tuple. So it will be just a tuple of two messages, like left message and right message, right? But we can't do much with this product. The only actually thing we can do is to compute a log PDF of that, because log PDF of such a product is just a sum of log PDFs of individual messages. We don't have mean, we don't have like variance, but this feature is we can use this to approximate this product with some method. So we have an access to these messages left and right, and we, for example, can use a Laplace approximation to return a Gaussian, or we can use a point like sample list approximation from semi. So basically, in order to use this product, which is not really a product but just a tuple, we need to approximate it somehow. And to do that, we pass this prod constraint, and we say that prod generic is an opposite of prod analytical. So by default, we use prod analytical. Prod generic just returns this tuple. And in this example, I say, OK, approximate this tuple, this product of messages with a sample list. Right? This is how we use it. Sometimes it is also might be useful to preserve some specific parameterization of your posterior marginals. Maybe it will be more efficient to have normal weighted mean precision posterior in your model. So you can use prod preserve type class, like structure, just to enforce special form of your posterior. So in this example, mu will have a normal weighted mean precision posterior parameterization all the time. Any questions? Good. So, okay. Here we have a block about free energy. So basically, as I said in the very beginning, on a very high level, actually we solve a variational problem. It happens so that this variational problem is equivalent to do message passing on factor graphs, but essentially it's still an optimization problem. And we want to check convergency of our like inference. We usually check free energy values. And for that reason, actually, that's why GraphAPL returns the model reference as its first argument, because from this model reference, we can get beta free energy observable. So we use score function, we pass beta free energy as its first argument and model as its second, and it returns an observable of future updates. So it's again an observable, right? Let me create it. So we subscribe on our beta free energy update, and again, we just print it in this example. And as you can see, every time I call an update, right, I get a new beta free energy value, and we can see that it converges nicely, and our inference actually works. And if I pass it again, I will get a new value of free energy, and again and again. And we may unsubscribe from it or subscribe, or basically it's up to you. What are you going to do with this information? So ReactiveMP just provides you this stream of values. And as I said, it's very necessary to unsubscribe every time. And yeah, again, if I will just call this function, it won't do anything. So this backend is lazy. So no one is listening to this free energy, so there is no reason to compute that. Okay, this is basically fundamentals, right? How to use that. And From that point, there will be some details about some extra features. So during model specification and during like this rule computations, we may need to have some additional information. Right? For example, if some rule is super complex, we may need some optimization library, or we need a differentiation library, or some meta information. Basically, we call it meta. Or another word for that is a context, some context. So as an example, we can pass some meta information to our message computation rules also in var block. This is a bit, yeah, looks strange. Okay, just looks strange. But in a sense, what we do here, let me just remove maybe this one for a moment. So we have an autoregressive model, autoregressive node written by Albert. And this autoregressive node needs an extra information in order to compute messages, right? It needs to know like variate type of our model. In this case, we pass multivariate. It needs to know higher order, right? So we can pass an order here. So it may be some, for example, 2, maybe 2, right? And it also has an extra flag, either IR safe or IR unsafe. And as I understand, the difference between them is that in some case, autoregressive node can be a bit faster, but do less accurate messages computations, or in contrast, it can be more accurate, but slower. But you can use this meta object and to pass any information you want in rules, right? For example, in Formulab.jl, some rules, they do extra adjusting of your covariance matrices. So for example, they add it's like tiny values on a diagonal just to make covariance matrix positive definite. Right. In some cases, it's not positive definite, and we can enforce this. Yeah, due numerical instabilities, we can enforce this positive definiteness. But in ReactiveMP.jl, you pass it as a meta flag. So either use this or not. So you can use tiny on that. You can skip, for example, or you can do adjusting based on how do you call it, SVD decomposition, right? So there are like plenty of options, but so some rules, they may have this implicit context where you, or for example, we have a demo on nonlinear node, and nonlinear node requires nonlinear function, right? And we pass this nonlinear function in meta object. And basically, meta object contains everything that is not a random variable. So that the purpose of meta object is just to pass some extra context to node. Or, for example, it can be a number of samples in your sampling procedure if some node uses sampling, right? So, but it is not limited in any sense. It can contain whatever like you want. Or, for example, for HGF node, it requires this Gauss-Hermite curvature approximation, and this Gauss-Hermite curvature requires number of points. It can be like 5, 9, 100, whatever. But so basically, we just pass it as meta information. Yeah, this is it about meta. And I think this is the last section about how to extend the functionality of ReactiveMP. So you want to try to run some complex model. You want to try some interesting stuff, and you need in message passing with factor graphs, you need to create node for that, right? And in ReactiveMP.jl, it exports node macro, and this node macro is very simple. It just accepts 3 arguments. The first one is the name of your node. The second one is type of your node. And the third one is an array of edges. So basically names. So first can be whatever you want. So it's just a structure. Second one is either stochastic or deterministic. We have only two types. And the third one is also like a fixed set of edges. In addition, with this set of edges, we can inform some alias names for that. For example, by default, normal mean variance has this out, mu, and v as its names, but there are also aliases for that, like mean and var. And these aliases, they are used in structured factorization specification. Now, in this Q factorization specification. So instead of like, we can say Q mean, Q var, Q out. But also these names are used in rule specifications later on. So there is a small note. In order to write this, we actually need to have this object, right? So I cannot just say that node ABC stochastic out in. I cannot do that because ABC is not defined, right? So ReactiveMP doesn't know what is the ABC. But it can be, for example, just so we can just create a dummy structure for that, and now it works. So basically just a Julia limitation. So in case if we don't have the structure, we just need to create it. That's it. It is also possible to use functions, right? For example, plus is a function in Julia, or multiplication is a function. We can use our functions as well. We just need to create again a dummy object for that. But syntax is a bit different. We need, in case of functions, we need to write type of, and this is basically it. So now I created a node that called foo, right? And in the same way, we create nodes for plus, for multiplications, etc. And yeah, basically, I just explained what it says here. So we have a function dot, let's say, and we can create a node type of dot. And okay, in case of dot, it's just a deterministic node, right? In case of many functions, it's just a deterministic node. And the only difference, not the only, but the difference is that it does not support factorization constraints, first. And the second, the way how we compute free energy is also different. That these are details. And we can use, so after this type of dot specification, we can just use it as a regular node in our model specification. So here a section about how we create custom rules. So okay, we created our node plus, right? Let's assume we created our node plus, but we can use it during our model specification, but during inference it will just fail because we assume analytical solutions for messages, right, by default. And in order to have this rule to compute a message, we need to write it down. And there is a amazing book, thesis from Coral about like factor graph approach to signal modeling. And it has this simple building blocks for Gaussians like plus, multiplication, etc. And according to this book, we have this simple rule for plus node, assuming that both inputs are Gaussians. The analytical solution for an output message is the following. So just a sum of means and sum of variances of incoming messages. And in order to write it down, maybe I can, yeah, because it's kind of zoomed, it looks odd, but okay. So here we have a rule macro. It accepts this type of plus as node, as name node, but in case of Gaussian, it will be like Where am I? But in case of like other ABC, it will be just, what happened? Okay, in case of like structure, it will be just ABC, but we have a type of plus. It has like this tuple of arguments. The first one is the name of an edge we want to compute a message for. So in this case, it's Z. It has this marginalization flag that tells us that our posterior actually respects the marginalization constraint. So it's a bit of more of a detail. I think it's better described in Ismail and Tai's paper about constrained beta free energy minimization. But this is, I mean, most of the rules, they just contain this marginalization flag. Another option would be moment matching for EP, but it's more like an advanced stuff. So next, we specify our basically arguments, needed arguments to compute our message. And in this case, we specify that we need a message over X and a message over Y, right? And these are of type univariate normal distributions family. So any Gaussian distribution, univariate. Might be normal mean variance, normal mean precision, or normal weighted mean precision. And we just write a simple function here according to an analytical solution, just sum of means and sum of variance. And this is our rule, right? And this rule macro, it supports, so in argument specification, you may require whatever you want. So for example, I can require a posterior over X, say X, and a message over Y. And this is done by these prefixes, right? So if you look on, let me change it back. If you look on the messages computation rules for some product, for example, this is an analytical solution for some product message. It depends only on messages, on edges. But mean field rule, they depend only on posterior marginals use. And this is the same for rule. For example, if variable has an M prefix, it means that it requires a message. And if rule has a Q prefix, it means that it requires a marginal over that edge, right? For example, here, yeah, this code looks odd a bit, right? But maybe I can just copy paste it. Okay. So yeah. So in this case, you can see that we require a message over out edge and a message over tau. But we can also do it like for mean field. We can require Q, right? And this Q can be also structured. So for example, if you do something like that, so you require a posterior over out and tau, like so the joint posterior, joint marginal. And the rule will be different, of course, just for demonstration purposes, but this is the general idea. So the rule, actually, in a sense, you can require both messages and posteriors, and you can require messages on all edges. And for example, some rule, let's say, again, normal mean precision, it can actually require message on mu as well. Right. For example, EP rules, they do require these inbound messages. But by default, ReactiveMP.jl will never call this rule. So it will require an extra pipeline modifications. So, I mean, it's possible, it's public API, but it's more like an advanced stuff. So by default, we just require messages, posteriors, or joint marginals. Any questions?
Hi, this is Bert. I think it's going really well, but how much more time do you want to take?
It's almost done.
Okay.
Yeah, basically this is about rules. This is, I told her already, it's, so this is a structured rule, requires joint queue. Yeah, there's one note that this specification of messages or marginals, they must be in order with this interfaces array. Just one limitation. So in this example, I cannot write m in 2, m in 1, just in case. Rules, they do have this optional meta object, right? We can dispatch on that, and we can compute different rules based on this meta object. So in case of Laplace approximation, we do something like one stuff. In case of Gauss-Hermite cubature, we do another stuff, and etc. And yeah, this is the last block. Basically, there is in this where clause we can use an extra pipeline option that allows us to modify default messages computational pipeline. So by default, we just call the rule and just send this message, right? But we can, for example, modify it and add some extra steps. So after we have computed a message, we can, for example, print it, right? We can print it, and we use this logger pipeline stage. It will just print it. Or we may have we may need some initial messages, right? So we initialize vague messages with this pipeline option. Or we, for example, if we don't have an analytical solution for our message, we can approximate it again with some Laplace method, maybe, or Gauss-Hermite cubature. So this is some extra steps, right, in our computational pipeline. So if I return to this coin toss model example, here I said, okay, let's log our messages around this beta node and messages around Bernoulli node. And as you can see, we just printed our messages, right? So we basically we can use it for debugging as well. So in this case, I can see that, okay, a message from Bernoulli node towards P has this shape, has this distribution, beta 1, 2. So that's it. And this is, yeah, that was all. That was all my presentation. Yeah, it was a bit long, I understand, but actually it's not even a half, I believe, of what is possible. So yeah, but I wanted to keep it short.
Okay. Thanks a lot. So how about if you take a 5-minute break, coffee, and then we come back for questions?
Okay, that's good.
Should I leave the recording running?
Yeah, we can always cut it out later. Yes.
Right.
Okay, we already have a question from Sam. Go ahead.
Okay. First of all, thank you, Dimitri, for the informative presentation. My question is about the schedulers in general. So here, the paradigm is completely different than the one we use in Fornalab, because in Fornalab we have this very explicit schedulers, right, for the message passing and everything. I can imagine that you probably don't need this scheduler in belief propagation, right? But in variational message passing, I think you still need some sort of scheduler. And I guess you force reactive message passing somehow to follow some sort of scheduler, right? And maybe not. So if this is the situation, could you please explain how do you do that? And if there is a way to get the schedule that you use during the inference? And if this is not the case, then how do you ensure that the inference is executed in a proper way? Because at least in my mind, there needs to be a schedule, for at least for variational inference.
Yeah, okay, so thanks. It's a good question. So indeed, for some product, you don't need this shadow, right? But for variational message passing, sometimes results are different. Depends on what order do you update. So the general idea of this inference backend is that it receives some update, right? And it immediately, so if node has all available information to send the message, it sends it. And when you start your inference procedure, you can imagine you have these observations, right? Just imagine you have this small squares, black. And when you pass this data point, the first node that is connected to this observation has all information to send the message. So it sends it, right? So, and this inference procedure, it starts from data points and it proceeds basically all the way up, right? So the first updates, they always happen near data, near your observations. Then it proceeds on higher layers, higher and higher layers, right? So this is kind of the general idea, because the rule is that it sends the message as soon as possible. But there is a hidden feature. It's not properly tested. Sometimes it fails, but you can enforce in a specific order of updates. For example, you get this data point, right? And you can say for inference backend not to update this value, but to update it at the end, right? So it kind of postpone this update. It waits for all updates to be executed, and then it updates your this particular. So it's the same order as in formula with step functions. Sometimes it may fail due to with structured factorization. Basically, I say it's hidden feature because it's not properly tested. It fails sometimes, but it should be doable in principle. But for now, it's hidden. So but in this case, if you enforce a particular order of your updates, you need to be sure that you initialized everything, basically, because what happens in ReactiveMP, if you forgot to initialize some marginal, it won't throw an error as in Formulab. In Formulab, you have these errors that some marginal is not available. But in ReactiveMP, there are no such errors because this marginal may eventually be available in the future, right? So inference backend will just wait, and if you don't initialize it, it will, as I showed in my example, you will just get empty updates. So in a sense that, this order, if you enforce an order, you need to initialize like either messages or posteriors. Basically, I don't know if I fully answered your question, but I don't know if there's a theorem or if it's proved or not, but I noticed then when you update your posterior marginal starting from closer to data points, you get actually pretty good results. But I'm not sure if it's proven or not.
This is, I see your point. Please, unmute. Okay, No, I see your point. This is okay. I'm asking this question specifically for the cases like if you want to do, for example, stochastic variational inference, sometimes we do not want to update some of the parameters, some of the random variables. We want to keep them and we want to update them all together simultaneously. So in this kind of situations, it might be a good idea to enforce reactive message passing to follow a certain schedule. That's why I'm asking this question. And the second reason is that it is often both for educational purposes and to understand how the algorithm works and sometimes inspect the algorithm better. It is good to see this scheduler explicitly. So this is also the second motivation. I think it would be nice to have this kind of features. So, and again, like just to make it clear, in the future, will there be such a feature to get this kind of a schedule that reactive message passing is following, to print it something like that, just to see what's going on inside and inspect further the algorithm?
Yeah, I worked on this scheduler, right, already. I think it's doable, and it's certainly possible to like print what happens even now. So as I said, this pipeline option, right, it allows you to print messages, but in the same way, you can actually print marginals updates. So you can, and you will just see in what order they do update, right? If you just print.
I have one more question.
Okay.
Wait, on this, I'm a bit worried now, because like if we have the full graph, usually for hierarchical models, you are in loopy structures, and in loopy structures, it definitely matters which where you're updating first. So how like is it or did you test it with Fornilab by like I don't know, in some hierarchical models like a hidden Markov model or somewhere, and then changing the schedule from Fornilab and seeing the inference results? Does it matter with the reactive message passing? It should matter, because like
I think I did that experiments like pretty long ago, and I think I got the best. So you can change this order in Formulab, and as far as I remember, maybe something changed already because I did it in the very beginning. But as far as I remember, I got the best results with ReactiveMP starting from updating from the bottom to the top.
Yeah.
So that's basically what ReactiveMP does. In Formulab, you can do the same, and you get the exactly same results. But if you update top to bottom, free energy will be just higher. But it probably depends also on the model you test, because I didn't test all of the models. But in my experiments, the best order was from bottom to top.
I